So hello everyone, welcome back to another video. In this video, we will discuss the problem of the day, and our problem of the day is insertion sort for singly linked list. So let's see the problem statement. Given a singly linked list, sort the list in ascending order using the insertion sort algorithm. So to solve this problem, we should have a prior knowledge to linked list and insertion sort. So now we will just quickly recap the insertion sort algorithm, and if you are already familiar with this algorithm you can skip this part and rest of us we can follow. So let's take a small example quickly to understand or to recap the insertion sort algorithm. Let's take value 4, 3, 1, 2. So if these four elements are to be sorted using insertion sort algorithm, the basic idea of insertion sort algorithm is we divide this array, our given array, into two imaginary subarrays. So at the first step, we will divide our array into two subarrays like this. So we will consider the first subarray of only one element at the first time as sorted. So 4 is sorted because it is a single element, so it will be considered as sorted. And the rest of the array, which is the next imaginary subarray, will be unsorted. And now we have to start our iteration from the first index of our array till the last index of our given array. So at the first iteration, we will compare this element with our last sorted element of our sorted subarray. So in our sorted subarray, we have the last sorted element, that is 4. So we will compare 3 with 4. So if we find the current element, that is 3, is less than 4, that means it is not following the ascending order. 3 should come before 4. So in this case, we will shift all the sorted imaginary subarray elements to one step right till we find the correct position for our current element, that is 3. So in this case we have only one element in our sorted imaginary subarray, so we will shift it once. So after shifting it will look like 4 1 2, and then we will place the current value in its desired position, which is 3. So now you can see these two elements are sorted. So from this point, our updated imaginary subarrays will be 3 4, which is sorted. This one is sorted, and the other part is 1 2, which is unsorted. So these are the two subarrays, imaginary subarrays. Now in the next iteration, our current will point to this, and we will compare it with the last sorted element of our sorted subarray, that is 4. So 4 is greater than 1, right? That means 1 is not in its desired position. So what we will do, again we will perform swapping of the sorted elements to the next indexes until we found the desired location for our current value, that is 1. So 4 will be shifted, then 3 will also be shifted one step to its next index, and thus we will find the updated array as 3 4 and 2. 4 is shifted in this place, 3 is shifted in the place of 4, and 2 remains at its same position. And now we will store the current value at its desired position, that was here. So by the third iteration we can see 3 of our elements are in their sorted place. So the updated imaginary subarrays are 1 3 4, which is sorted, and 2. So we are left with 2, and as I have said, we have to iterate till the last index of the array. So we will iterate for the last time. Here the current element is again less than the last stored element of our imaginary sorted subarray, that is 4. 4 is greater than 2, thus we need to swap all the values to the right index till we found the desired location of our current element, that is 2. So let's perform the swap operation quickly. 4 will be swapped, 3 will be swapped, and 1 is less than 2, so this is the desired position of 2. Thus the updated array will be 1 3 4, and we will store the value of our current index at its desired position. So this was our final iteration, and we can see we found a sorted array. So this is how we can sort our array using insertion sort. Now coming back to our problem, that is perform this insertion sort in a linked list. So how we will implement our insertion sort in linked list? Let's see. So let's take the same example for better understanding. So let's say this is our linked list and we have to sort this linked list. So we will proceed by following the algorithm of insertion sort which we have discussed just now. We will create imaginary partition. The first part will be the sorted one. So let's say the first index or the first node is already sorted and the other nodes are unsorted. So we have to iterate over each node and have to place all the nodes in their desired location by comparing them with the last sorted value. So as this is a linked list problem, so we can't go to a particular index at any time and get their values. So it is not possible. In this case, we will take some reference node to keep a track in our given linked list. So at first we will take or create a dummy node and we will assign a value of 0 in it. This dummy node will be the head node of our given linked list. So if the base address of the head of our given linked list was 1000, in the dummy node dot next we will store 1000, and thus this node will point to this node. All right. So now the question arises, what is the use of this new node, that is dummy node? We will use this dummy node to simplify our operation in the linked list and also to avoid some edge cases. So by this new node, we will ensure that our insertion happens in the middle of our linked list or the sorted part of the linked list, not at the beginning of our linked list, because all the elements, if you see, are greater than 0. So anyways, they will come at the right side. If we follow the ascending order, they will come at the right side of our dummy node because the value of dummy node is 0. So all the elements are greater than 0. You can also assign the value of this dummy node as -1. So all the elements are positive and anyway greater than -1. So the insertion will never happen at the beginning of the linked list. And next we have to take a reference node which will store the last sorted node of our linked list. So the last sorted node at this time, at this point of time, is 4 only. So we will store this in a reference node, because according to the insertion sort, we have discussed that the last sorted element is compared with the current element, right? And then if it is greater or lesser, we perform further operations. So we have to store it. That is why we have used this node. We will store the last sorted element every time after updation of our node. But at the first case, we can see the last updated value or the last sorted value is this node, which is our head node of the given linked list. So we will simply store it. And whatever the base address it is storing, it will store the same base address. So I hope we are clear with the use of this node. Next, we have to create a reference node which will points to the current node. So if you have understand the algorithm of insertion sort, you can relate. Each time we are comparing the last sorted value with our current value. Thus we have to store the current value as well, current node as well. So we will simply store the current value in a new reference node, and whatever the base address it stores, it will store the same. Basically, it is pointing to the next node. So it stores the base address of the next node. I hope you are clear with all that logics of linked list. And now at last we have to keep a track on our sorted part, right? So for that we need another reference node. So basically it will be initiated with the value of dummy node, which is by default pointing to the head node of our given linked list. So I think everything is clear. If you have any doubt, you can repeat the video. But if you want a quick recap, this is a dummy node which will avoid the edge cases and insert at the beginning of the linked list. This is a node which will use to keep and track in our sorted region of our linked list. Another reference node we have taken to store the last sorted value, and at last we need another reference node which will indicate the current node in our linked list. So we are done with our nodes, and yes, these reference nodes are important to perform further operation in our linked list. So that's all we need to perform insertion sort in our linked list, and the rest of the operation will be exactly same as we performed in the case of array. So each time we will compare the last sorted value with our current node value, and accordingly we will find the best position of the current node in the sorted part of the linked list, and we will swap the values accordingly. So I hope I made this program a little bit simpler. So now we will quickly get into the code. But before that, let's discuss about the space and time complexity as well. So we will iterate through each of the node in a given linked list. So the time complexity for that will be big of n. And then we also have to iterate in the sorted linked list region to find the best position of our current node value. In that case also we can iterate for n number of times. Thus, if we find the total time complexity, it will be big of n square. And now coming to the space complexity, to perform this operation, we didn't use any data structures to store the input data, and thus the time complexity will be constant, that is big O of 1. So if we see, we have met our expected time complexity and space complexity as well. So now let's get into the code. So as we have discussed, we will create some reference node. So node dummy to handle the edge cases. We have discussed all these things. So please check it out before entering to the code part. And in the dummy.next, we will store the base address of our head. Two more reference nodes, that is current, that will keep track to the current node of our linked list. So we have initiated our current with headref.next. That means the second node of our linked list. If you remember, while we are performing insertion sort in our array, we are starting our iteration from the first index of the array. So here also we will start our iteration from the second element or the second node. The array is zero base indexing, that's why we have started from 1. And another reference node will store the last sorted element. So we have to check the last sorted element or the last sorted value of the node with the current node value, and it will be assigned with the head ref for the first time. After this, we will start our iteration from the current till it becomes null. So all the operations are exactly same as we performed in array. So here also we will iterate till our current is null. Now can you guess the operation which we have to perform? We have discussed it, right? We have to check if our current data is less or greater than the last sorted data. So simply use the if condition and check if the current dot data is less than last sorted dot data. If this condition is true, that means we have to find a perfect location for our current data in the given linked list. So we have to iterate for that in our sorted region. And we have discussed that to keep a track in our sorted region, we have to take a reference node. So we will take node prev equals to, we have initiated it with the dummy value. You can check all these explanations in the first part of the video. And now we will iterate in our sorted region. So while prev.next.data is less than the current data. That means until we found a data in our sorted region of the linked list which is less than the current data, we have to swap them. We have to swap them to the next indexes. In our array case also we have done this. So we will do prev is equals to prev.next. So by this way we will find a perfect place for our current node data, and after that we have to update our last sorted, because now after swapping the last sorted will be changed. So we will change it by current.next. So we have stored our current.next in last sorted.next, and in the current.next we will store the value of previous.next, and at last we will update the previous dot next with our current value. So we have inserted the current value in its desired position, and after that we have to update our current also. So our current will be pointing to the next node of our last sorted node. So we will simply store current equals to last sorted dot next. So we are done with the part where we will find a suitable spot for our current data in our linked list and place it in that position. Now in the else part, that means when the current data is greater than the last sorted data. In that case, we are not performing any operation, we are not swapping anything. So in that case, we were simply iterating further in our linked list. So our last stored value will be our current, and our current will be pointing to the next node. So current is equals to current.next. And thus we are done with all the operations. Now simply we have to return the node. So we will return the head of the node, but we have created a dummy node as our head of our given linked list. So instead of returning the dummy node, we will be returning the next node of our dummy node, which is basically the head of our given linked list. So simply we will return dummy.next. If you want to see this visually, let's refer to the example again. Here we have created this dummy node. So the final linked list will be 0 as our head node. It will referring to the smallest value, which is 1, and it will refer to 2, then 3 and 4. So this will be our final linked list, but this was not the part of our given input. So we will not return this. Instead of that, we will return the base address which this node is storing, and thus we will get our expected output, that is from 1 to 4 as the sorted singly linked list. So let's quickly compile and run our code. So we have encountered some compilation error. These are, I guess these are some typing mistake. The variable we have taken is cur. So it will be cur. Basically by this variable cur, we are referring to the current node only. Anyways, let's compile and run again. Yeah, so compilation is completed. We are getting our expected output. Let's submit the code. Yeah, so guys, we have successfully passed all the given test cases. We have discussed everything about this problem. We have discussed about the time complexity, space complexity, how we will approach insertion sort in the array as well as singly linked list. So I hope you like this video, and if you have found anything helpful in this video, please like, share and subscribe my channel, and let's get back tomorrow with a new problem.